Hi, I'm Elijah.
And I'm Casey.
Currently, around 300 million people live with visual impairments. To help these people, we have designed a system that we believe will allow them to gain back some of their independence and safety through an increased awareness of their surroundings.
Current assistive technologies are extremely simple and low tech. Take canes, for example. With a cane, someone can tell that there's something in their general reach, but they have no idea what it is or what's beyond the reach of their cane.
To expand on this technology further, we have designed a device based on the same cutting edge technology found in self driving cars that will detect obstacles and objects around the user and alert them through auditory cues.
Let's see how it works. The base of our device is a pair of recycled sunglasses without the lenses. Mounted to them are two webcams that we salvaged from broken laptops at our school. They are mounted using a custom 3D printed bracket. The webcams connect into a USB hub over a USB protocol. The USB hub is connected to a long cable that connects to the processor and the audio component. Currently, we're using a laptop for this part, but in the future we want to make it more portable, maybe using a Raspberry Pi and earbuds.
This device was incredibly cheap to produce. The only component we bought was this $7 USB hub. Our goal was to democratize this technology so that it can be widely accessible to those who need it.
The hardware is simple by design, but the real strength of the device comes in the software.
Our algorithm can be essentially broken down into 6 key modules. First, when the user clicks the mouse, the two images are taken, one for each camera, in quick succession. Ideally, these images would be taken at the exact same time, but due to bandwidth limitations from the webcam and the USB hub, we have to take them with a delay of about 1000 milliseconds.
Both of these images are individually fed into a convolutional neural network that was trained using TensorFlow on the Microsoft Common Object and Context dataset. This dataset contains over 300,000 images and allows the device to detect 80 different objects with extreme accuracy. This ranges from things like chairs to pets. It's especially good at detecting people and cars, which we determined to be the most important things to avoid. This generates two sets of images, which each have their own sets of objects with location and size data.
The next step is to match these objects across the two images. We know that there are 5 people in this image and 5 people in this image, but we need to know which are the same 5 people so that we can calculate depth. To do this, we created an algorithm that takes in 4 factors: position of the object in the frame, relative position to other objects, size of the object, and object type, and it weighs them in different amounts to generate distinction scores for all objects to tell how different they are from each other, and it matches the ones that are most similar. In doing this, we create one list of objects with both a left and right component.
Now that we have the object pairs, we can finally determine depth using the difference in horizontal position between the two pictures. We originally thought this would be simple through triangulation with similar triangles, but this ended up being not very accurate when the objects were close to the camera or far away from the camera. This was very unexpected, but we decided to adapt. We made a scatter plot using hundreds of pixel disparity values at known depths, and we ended up with a regression that more closely followed the inverse square law. Using this regression in our calculations, the device was much more accurate at all of the extreme ranges.
We are also able to determine the angle of the objects based on their position in frame. This, in combination with the depth, allows us to plot the objects in real-world space in a manner similar to polar coordinates. This is the true output of the device, and then it can be conveyed to the user in different ways that balance speed versus understandability. The next two modules that we have are both focused on conveying this spatial information to the user through speech.
To make communication of this information faster, we group nearby objects of the same type using their real-world positions. So instead of the device saying one chair, one chair, one chair, we can just say 3 chairs.
We then communicate this information to the user through text to speech. We try and do this in a concise manner that is also very understandable. So we round distances to the nearest half meter, and instead of saying things like 42 degrees, we could say slightly right or directly ahead. This will not only increase the speed that we can say this information to the user, since we don't have to say long decimals, but it also makes it quicker for them to understand and begin to build a mental map of the environment.
One car 3.5 meters slightly left. One person 2.5 meters ahead. One chair 2.5 meters ahead.
To test the accuracy of our device, we built a physical representation of its output map, complete with distance markings. We devised 4 different scenarios that would put the different aspects of our device to the test. These scenarios were one person, a group of people, furniture, and cars.
For each scenario, we randomly distributed the subjects within the specified range. We then recorded if the device successfully placed all of them within 0.5 meters of their real location. We repeated this many times for each scenario, shuffling the participants' location each time.
From this, we were able to create sampling distributions and confidence intervals. With one person 4 meters away from the device, we were able to say with 95% confidence that the device will correctly identify them 90% of the time. With a group of 3 people at a longer range, we can say with 95% confidence that the device will correctly identify them between only 74% and 93% of the time. Cars and furniture performed much better, and we were able to say with 95% confidence that the device will correctly identify them 95% of the time.
From our testing, we concluded that our device struggles the most when dealing with large groups. This is likely due to both obstruction, for example when one person blocks another person, but also due to the low resolution of our webcams. If there's a person whose hand is the only thing that's visible, our algorithm may still be able to pick that up. But when that person is far away, suddenly that hand is only comprised of a dozen or so pixels, and it becomes much less likely that our algorithm will correctly identify it.
Our device really exceeded our expectations. All the components worked together, and they produced a pretty accurate representation of the environment. Our device was found to work best with people and cars, even if they're not completely in the frame. It also works best with objects that take up a larger portion of the frame, and it can map them much easier.
It struggled to consistently map larger groups of objects, but we think that even at its current level, it is still enough to help someone accurately build a mental map of their surroundings.
Currently, it can detect 80 different types of objects, but we plan on teaching it more through transfer learning. But first, we'd want to consult a visually impaired individual so we can know what's most necessary.
We believe that the objects we have now are a great baseline. Since the dataset comes from self-driving cars, most of the objects are based on things that are either on streets or could run into streets. This means that we're great at detecting things like street signs and also things like dogs.
We have many plans for ways to improve our project. Our main problems came from the cameras that we used. We loved that they were free, but they had 2 main problems. One was the bandwidth. Because of the bandwidth, we couldn't send both the pictures at once over USB 2.0, so we had to capture them at different times. This is fine for static objects, but objects that were moving across the screen, they ended up in 2 different positions between the images, and so the depth calculations were completely off. The other problem was the low resolution, and this just limits our maximum depth that we can detect objects at. It was about 10 meters for people and 20 meters for cars.
Our solution to this involves buying better cameras. This will, of course, increase the price of the device, but we believe it will be worth it. When buying better cameras, we would look for both a higher resolution and a wider field of view, which in combination will allow us to cover a much wider area.
The second half of our solution involves Raspberry Pis. The fact that our device is tethered to a computer right now doesn't help us if we want to help people regain their independence. The second generation of our device will use 2 Raspberry Pi Zeros, which are basically lightweight computers that can be run on a small battery. The Raspberry Pis will connect through Bluetooth to the user's phone, where all the processing will be done. Each Raspberry Pi has a dedicated camera port, and so we don't need to use USB 2 protocol. So the lag between the 2 images will be completely eliminated. Another issue with our device is that while it can detect singular objects like chairs or trash cans, it cannot detect structural aspects of the environment like stairs or a curb. This is almost impossible to achieve with traditional computer vision, but we have an idea.
When we have 2 images taken at exactly the same time, we can use epipolar lines to create a generalized depth map for the entire image. This will allow us to train an additional convolutional network to detect structural aspects from this depth image, dramatically increasing the usefulness of the device.
We plan to continue working on this project in the future. Thank you so much for watching.
Thank you!
Now for one last demonstration.
Judge detected directly ahead. Thank you.